Thanks for listening to the notes today. We're going to take a look here at Unit 4, Notes for D, and we're going to talk about the rate of change of a linear function. So a few things to keep in mind, and these are items 1, 2, and 3 on this list. Linear functions increase or decrease at a constant rate. That's what we're going to refer to as our rate of change. Another way to think about this is a constant rate of change because it's the same. So not only can we call it ROC, but we can call it a constant rate of change, a CROC. I'll refer to it as a CROC at times as well. The rate of change for a linear function is the change in y over the change in x. And another word we're going to use to refer to this is the slope. Okay, so in this yellow box here, you're going to see that there's a few different ways that we can represent these, or a few different ways we can describe it, but they're all kind of describing the same thing. Which is the change in the dependent variable divided by the change in the independent variable, which is the same as the change in y values over the change in x values, or the change in the common differences of the x values and the common differences of those y values. Now we're going to take a look at these rates of change numerically. So as we've been doing, I'm going to look at the differences between my x values, and if you look on the left, my x values are increasing by 1. On the right, my y values are increasing by 5. So if I use that delta y over delta x, that is a positive 5 over a positive 1, which means my constant rate of change, or my rate of change here, is 5 over 1. Another way to express that is simply 5. Taking a look at example 2, we're increasing our x values, or our independent variables, by 2 every time. So it's plus 2, plus 2, plus 2. My y value is decreasing, so I'm subtracting 1, subtracting 1, subtracting 1. So if I look at my delta y, that is negative 1. And if I look at my delta x, that's 1. Anytime you have a fraction, you want to see if you can simplify it. In this case, I can't simplify negative 1/2 anymore, so I'm just going to leave it as negative 1/2. And it is important that we keep the negative, because that is a negative divided by a positive number. Okay, a couple of special cases here are 3 and 4. Example number 2, my x values are increasing by 2 between every value, but you'll notice that my y's are not increasing, so I have a value of 0 for my delta y. My delta x is going to be a positive 2. 0 divided by 2 is going to give me 0, because 0 divided by any number is 0. You'll notice that the rate of change is 0. Okay, we have y values that are a little bit different here. I'm increasing by 6 here, and I'm increasing by 4 here. That's not really going to make a difference that these are different. What is important is, let's just take that first, delta 6 to start out with. It doesn't really matter what my delta y is on this one. My x value is not changing, so I'm trying to divide by 0, which gives me an undefined rate of change. There's no way to divide by 0, so there's no way to define the rate of change of this function, because what I'm really looking at, if I graph this, is a vertical line. It's going to be going straight up and straight down, so there's no way to calculate how much y changes, because x never changes. On the next page, if I'm trying to do this algebraically, meaning I'm trying to actually calculate the difference, what I'm going to use is the slope formula, which we're going to refer to slope as m. And that is going to be the difference in y coordinates over the difference in x coordinates. This order is important. Normally it's expressed as y2 minus y1 over x2 minus x1. I think it's a really good idea on these to actually label your point. So for this first example, this is my, x1 and y1, and then I have my x2 and y2. This is just going to help keep things in order. My other piece of advice here is, every time you do this, it's really easy to mix up your integer addition and subtraction. So I know I'm going to subtract those differences, and it's nice to have parentheses on both, but a bare minimum would be to have parentheses on the second set, because if that ends up with a negative value, you're going to want to keep those negative signs in order. So what I'm going to do here is I'm just going to do y2 minus y1. So I look at my labeled points, and I'm going to do 2 minus 2. And then I'm going to do x2 minus x1. And I end up with 2 minus 2 is 0. 1 minus 4 is negative 3. So my rate of change here is 0. So 0 divided by any number is 0. So let's move over to example number 6. And you want to be methodical about these, because a lot of the problems that we encounter here are going to be in the details. So again, I just label all my points, x1, y1, x2, y2, and then I just set up my slope equation. Now it's kind of a little mindless task just to plop these things in. So my y2 is negative 1 minus y1, which is 5. My x2 is 2. My x1 is 0. So now I can just say negative 6 over 2. And that's going to give me a rate of change of negative 3. So we're just going to call it negative 3. All right, so try the rest of those examples on your own. Well, I shouldn't say the rest of them, the last two examples on your own, and let's see what we get for our rate of change. Okay, looking at number 7. Again, I like to use the parentheses, and you'll see why on the denominator of this fraction. So I have 7 minus 3 up top. In the numerator, that's going to be 4. 2 minus a negative 1 is the same as having 2 plus 1. So I end up with a positive 3 in the denominator, so that is 4/3. And we're just going to leave it like that, because when we graph these, it's going to be much easier to graph a fractional slope than it is going to be to graph a decimal. So don't change this into a decimal at this point. And then on 8, when I calculate this, I'm going to end up with 14 over 0, which is undefined. Okay, so now we're just going to look at these slopes on a graph and just get an idea of what type of slope we're looking at. And what's important to remember is the rate of change is going to be referred to as the slope of the line. So when we look at these linear functions, when we're defining the slope, we're reading it left to right. So what we're trying to do is see if the function is increasing, meaning it's going uphill as you're going left to right, which would be a positive slope. So this first example would be an example of a positive slope. Okay, and we'll talk later about how to actually calculate that slope from the graph, but for right now, we'll just say that that's a positive slope. Here, as I'm going left to right, the function is decreasing, so it's moving down and to the right. That is a description of a negative slope. And then here, if you move from left to right, nothing's really happening. My function isn't increasing or decreasing, so it is possible to have a 0 slope. And we actually calculated those, and we saw what that looks like on a table as well. And finally, as I'm moving left to right, well, my function's going up forever, and it's also going down forever, which is kind of an odd situation. So this is what an undefined slope would look like, because there's no way to define this slope, because it's both increasing and decreasing, which is kind of odd. So we're just going to say that's an undefined slope. So now you have enough information to complete worksheet D, which will be your homework today. I'll check that in class on Monday. Thanks for listening.